This is Tim Haggerty with the Virtual Training Company, and we're doing our C++ fundamentals videos. We are going to take a look at a brand new concept, a brand new fundamental for C++, something you did not ever see in C before, and that's called a function template. A function template allows us to create a function that will accept different types as input, not just values. It used to be when we had to write a comparison or a sort or something like that, we'd have to write one for strings and one for characters and one for integers and one for floats and so on. Well, now we can use a function template, and when we use this template, we can say that when this function is called, that it can take in different types. It's very, very powerful. For example, down here we have a example, and the template class identifier function declaration, that's what it looks like, and template type name identifier function declaration. They're basically identical. There's no real difference in them. I think it was for compatibility with a different version or a different flavor of language that was brought into C++, but we'll just use the term class just to keep it consistent. So down here we have template, class, and then my type, and you're going to find out that that's usually just a capital T for type. That's most of the time what they use here. Then the actual definition is here. My type, that's going to be the same value from there. So if that's a capital T, or in our case just my type, that will come through here, and that is saying that the getMax function, here's the actual function that we're defining here, that, or declaring at this point, that getMax will return whatever the type is. And here's the type from up here. So let's say that this is an integer when we use it, and we're going to use it in a minute. I'll show you some code here. Then the getMax will return that same type. It will also take in two values, A and B, also of this particular type that gets used. In this case, the word my type, that's just the identifier, but that will be an actual type, like an int or a char or a float or a double or even a class. And we're going to see that in a couple of screens here, or a couple of videos actually, that there are class templates too. But right now let's stick with functions. So we have the type A and B are going to come in, and then this is simply going to do a return, and it's going to do a tertiary operator, and it's going to do the test, is A greater than B, and if that's true, return A. If it's not, return B. So either A or B will come back out of this, one of these two values, the bigger one, because it's called getMax. And when that return is performed, it will come back as whatever this type is that's coming into us. Okay, very simple. Let's go over and take a look at some code here. And here's all the standard stuff. And here's our template. Template, class T. So there's that T that I told you about, and the compiler knows that this is a template. And here's getMax, and it gives us a little information that getMax will return a T. It will take in a T. It will take two T's, whatever they are, A and B, on the way in. And here, getMax will create a result, and then the result will be equal to the comparison operator, and then we'll return that result. Basically just what we showed before. Now here it is in use. Here we set up a character A. We set it equal to a constant A, B, and X is going to be our return value, also a character. We set an int of 5 and 6 and a long of 10 and 5, just for numbers to put in here. Now here's how we're going to use this thing. Here we say K is equal to getMax type int. See the less than and greater than? Those are the characters you want to watch out for. So getMax is of type integer, and here's our I and j. So when this gets used up here, the getMax, we've said that this is going to be an int. So now wherever you see the type name T, replace that with int. And the compiler does all this for you. You don't have to do this. That's the great thing about the templates. Here we use it for longs, and is the getMax of longs, L and M, which are our two guys here. And then we use the character one. But you know what? There is an implied template version here as well. We can, if we leave off this int and long and so on, the compiler will figure it out. The compiler can look and see that A and B and X are all characters. It understands how the template is created using the same class all over, and that will imply characters, and that's exactly what it will do. And then here's just the cout that will print the output. So let's run this. And 6, 10, and B. Those are the larger values of all three of those. It did exactly that with just one piece of code. So those are function templates. Very powerful, something to take a much more in-depth look at as you start to get into really doing some programming beyond fundamentals. So a great way of separating your ideas from your actual code so that you can have one idea and let it work on multiple different types. That's really the power of templates. And this is Tim Hegarty again with the virtual training company C++ Fundamentals. Now we're going to look at class templates. We just looked at function templates and saw how to use those. Now we're going to look at class templates. And it gives you just about the same functionality. It's really allowing us to create classes without specifying the types that will be used as input to those classes or stored in the classes and so on. For example, there's a template, class T, they like T again, and this is now going to actually create a class called myPair. Now myPair will have two values in it, and they will both be of type T. So you can see that right there. Type T, that's going to be this same T, whatever this gets brought in when we create the class. Char, int, float, double, whatever. Then we have our public access specifier, and we have our constructor for myPair, has the same name. We'll take in two T's, first and second, are going to be of the same type, and then we're just going to define values. Here's our little array. Sub 0 equals the first one, value sub 1 equals the second one. So that's our constructor, very, very simple. Let's take a look at a little bigger piece of code with this in it, and here we are. We have our template class T right there, and here's our class definition, myPair, and there's A and B are both of type T, whatever that will be. Here's our constructor using the T types just like we just looked at, and now we're going to have a member method called getMax, and it will return type T. Also specified from there. These are all the same T. Whatever they happen to be, char, int, float, whatever, they will get turned into that during the running of the program. All right, now down here we have, again, the template class T. We have to specify that again so that we wrap this properly, because now we're going to create the member function getMax by using the return. It's the myPair class of that type. Got to specify that type in there again, and then getMax is the actual function name. And inside getMax, we will have, as we define getMax here, we will have a return value of type T, whatever that is. The return value is again equal to the comparison, A greater than B. If it's true, send back A, otherwise send back B, and then return it. Or you just put that into return value and then you return value. And here's main actually using that class and that member method. Here's myPair. We're going to create of this class. That's the class name. And there's the int. Int is going to be all throughout here where T is. It'll be changed into int. And myObject is the actual name of the instantiation of the myPair class. And we're going to stick two values in there. And those two values, that corresponds to our constructor, first and second, that we had up there. So first will be 100 and second will be 75 in our little example. And then we will do the console out of myObject.getMax. So we'll take myObject, use its method getMax, and getMax understands that it is supposed to be working on integers because it knows the class type, and then just an end line. All right, let's see if this actually does it. And 100 was the larger number of the two that went in. 175. So it works exactly the way we thought it would. Pretty simple, and we hoped it would function properly. So get a very good understanding of these templates and how these templates can work by looking through this sample code and changing this up a bit to use some characters, modify this code a bit and use characters and floats and pass some different numbers and see what's happening there so that you can see how the template classes are working. Hi, this is Tim Hegarty with the Virtual Training Company. We're talking about C++ fundamentals, and we've been talking about function and class templates over our last couple of videos. And now we want to take a look at a use for templates. And here's an excellent use for templates. The standard library containers are created with templates, and a container can be considered to be a class with the main purpose of holding a collection of objects. There are several different kinds of containers. We're going to look at two of them here. The rest of them work in a very similar fashion, but the big difference is the timing, how difficult it is for the compiler to do certain things, like linked lists, vectors, arrays, things like that, and reallocating memory and such. The containers are implemented with class templates. So a template, remember, can be used on just about anything. So we can have a vector, which is basically a dynamic array. It looks like an array that we're used to in C, except that you can dynamically change the size of it, tuck things in the middle, move stuff around. The things, though, can be any type. Characters, ints, floats, doubles, other class objects, whatever. It doesn't matter because it is implemented with templates. An associative array is a map. The standard library containers is a map. There are queues. A heap is called a priority queue if you're going to implement a heap of memory. A stack, popping and off the stack and pushing onto a stack, is called an associative array. And then a linked list is just a list. We're going to take a look at that. And trees are sets. So you can have a binary tree implemented as a set container. Now let's take a look at a vector for a second. A vector is essentially a resizable array. You use the brackets just like we're used to in normal C to access elements of the array, but there's other ways of getting to the information as well. There are other useful methods. For example, front. So we would use whatever our vector name is we created. Dot front would give us the first element. Dot back would give us the last element. Doing a dot pushback would add a new value to the end of the array. Doing a dot pop back removes a value from the end. And a dot size, well, obviously that's going to give you the size of the vector. Now let's go take a look at some code for vector and see what we have here. Here's our vector. We have to include the IO stream and vector. You include vector, you don't use the .h with it, so that you pick up the code that implements the templates of vector. Now here is the creation of a vector, and this is going to be a vector of integers. And see that class standard, : vector, that's our scope, vector, type name, they use ty, and a type name ax. Now here we are going to use integers. So we're going to create a vector of integers and call it example. And then once we have that created, we can start to work with it. So here we have a for loop, and we go from 0 to less than 5, and we do an example dot pushback of that value, I, 0, 1, 2, 3, 4. So we'll load up our little example vector. If the example is not empty, then we'll dump it out. Or we'll say there's something in there. And then since I know that there's something in there, we're still in this if, we're going to go ahead and dump it out. We'll start a new quickie loop that goes from 0 to less than the example.size, so we know how many elements are in there, and then we will print out each of those elements. Now we're going to create another vector. Remember, this is a great thing about C++. We can declare new variables down here just by doing them wherever we want to in the code. Couldn't get away with that in C. And we have a vector of integers, another vector, creates another vector, and here we're going to load it up again the same way. Another vector with using pushback, so that will load those values onto the end of the vector, and we will compare the two. Now we know we loaded them the same way, 0 through 4, so we know they have the same stuff in them. If the example is equal to another vector, now that could take some time depending on what these vectors are made out of, because this equality operator is a special operator in vectors that will go through and compare both vectors, every element one by one, and that can be very expensive in CPU cycles depending on how big those vectors are and what they're loaded up with. So this will go down through and compare 0, 1, 2, 3, 4 with each other, and if that is true, we'll say they're the same. And then we'll go through and we will dump out our example size again to show what's in there, and then we're done. So let's give this a quick run so you can see there is something in there. There's 0 through 4, they're the same. There's 0 through 4 again, so it does exactly what we thought it was going to do, and that's using a vector. All of the other containers work the same way with this template example. And remember, you wouldn't just use int in here, you could use anything. You could have a vector of characters, a vector of of strings, a vector of classes, of whatever makes sense to have a dynamic array that we can use this way. Now, let's take a look at another one here, and this is a container list. Now, a list container is a doubly linked list. Each element in the container, in the grouping of them, has pointers automatically created as part of the template, which are linked to each other. Each element links to the one previous to it, except for the first one, of course. It has a marker that it's the beginning, and each one points to the next one in the list, and of course, except for the last one, where it points to end, that there is nothing else after the last one. A list container is faster than a vector for inserting new values, because you can just move the iterator, which is how you get from one point to another inside a list. You move the iterator, and then you can do an insert and put a new value in there, and it adjusts the chains. If you do an insert on a vector, it shuffles everything down in memory to make enough room for the insert, and then it puts the item in. So that can be very slow depending on where you are in the vector and how large the item is that you're tucking in the middle. So a list is much better if you're going to do that kind of work. We also have some unique methods here. We have front, which will give you the first element, back, or dot back, will give you the last element. A push front and push back will add to the front or the back of the linked list. And then you can also do a pop back and or pop front, I wanted to say there, pop front and pop back, will remove values from the front of the back. And there's some other special methods on list, like sort, so you can sort the entire list and things like that. So that's the fundamental of containers, and there's half a dozen different styles of containers in your standard library, and they implement different kinds of structures, as you can see, whether they implement trees or linked lists or associative arrays or dynamic arrays, so on. So that is the concept of containers. This is Tim Hegarty with the Virtual Training Company VTC C++ Fundamentals video series. Let's take a second to talk about function overloading. Function overloading is having multiple functions with different parameter lists, and it's giving one function. It's going to do the same work, basically different parameter lists. This allows the function to accept various kinds of parameters, but it basically performs the same task. Let me show you here in a little piece of code. So here we have the add and display. Notice that they all return the same value. They have to return the same thing. In this case, it's void. All three of these functions are going to do the same work and have the same name, but they have different parameters to them. So add and display that takes two integers, an x and a y, there at the top, will spit out VTC tutorial integer result x plus y. And that's the same thing that add and display of doubles will do, and add and display of floats. They all perform the same operation. The compiler at compile time makes a series of decisions based on the parameters that are being provided in the function call. So if a function call has two integers in it, the compiler looks through all of its add and displays and says, which one do I have that has two ints in it? And it finds one and then picks that one. If you don't have a set of parameters available that match what you're trying to call, the compiler will go farther through a more complicated list, do some promotions and conversions as it can to try to find something that matches what you're trying to do. If it comes up with two of its rules that match through different types of typecasting or conversion, then it doesn't know which way to go, and you will get an ambiguous reference. And then you'll have to do your own typecasting and force it into which of these overloaded functions you want to try to use. So that's function overloading, is using the same name for the function but providing different parameters. This is Tim Hegarty from VTC doing the C++ Fundamentals video series. We want to talk about I/O streams for a minute so that we can communicate with the outside world, get information in from the keyboard or from files, or even we can create streams out of information that is already in our program, like strings. Strings can be treated as if they wwere streams and read off into integers and have formatting performed on them. That's a little deeper than a fundamental, but it's possible. The streams, iStream and OStream, input and output, are both derived from iOS, the iOS class. The iOS class is derived from the iOS base class, and the iOS defines the templates of iOStreams, and the iOS base defines the non-templated methods of the class. As we can see, iStream implements input operations, OStream implements output operations, and the way we normally see these is by using formatted input and output, and that's most often performed with two operators, one called the extraction operator, which looks like a double greater than, and the insertion operator, a double less than. Let's take a look at some simple code. Here we're including iOStream so that we pick up the streams, and CIN and COUT are created, and that's just like our old standard in and standard out that we used to have in C. Now in C++ we have these streams, and there you see it's part of standard OStream and then standard COUT. So COUT is a derivation of OStream, and it is the standard output. So here we're going to enter a number, and there's our insertion character, and that is going to say enter a number to the screen, the COUT. Then we are going to use the extraction and extract a couple of characters from the CIN, the iStream. As you can see that's an iStream there. And we'll put that into N, which is our integer, and then we'll put out, you have entered, and then we'll put N, and you see how this flows through here to get to the output with this insertion operator, and then that's an end of line, and we'll just simply put a new line out to the screen. Now we can put some special iOS base operators like hex. So if we put extract information from CIN, run it through hex, and extract that to N, it will do a hex conversion for us into an integer, and we can see that when it runs it back out again. With a word here, we will set the width on the CIN so that we will only allow 10 characters to come in, and then we will after we set that limit on here with the width method, we can then use CIN and extract to a string. Once we extract that to our string, which is only 10 characters long, we can say the first 9 characters are, and we can run string to the COUT and of course our end of line. So let's run this, take a look at it. We'll enter a number 47. You've entered 47. Let's enter a hexadecimal number, and we know an easy one is FF. Decimal equivalent is 255. We know that to be correct, and we'll put a word in. The first 9 characters are compiler, and we have communicated with the outside world using iOStreams, standard in and standard out. Now, of course, there's a lot more to streams. We have file manipulation and all of that, opening and closing files and such, which is very similar to the methods that we've used in the past, but much more modular now in C++. So we have methods and operators that work on file streams. But again, a file stream is just exactly the same thing that we've seen, because CIN and COUT are just file streams that have opened the keyboard or opened the screen. So the fundamental of the iOStreams applies all the way across the board. C++ is much more generic along those lines. This is Tim Hagerty with VTC, and we're talking about C++ fundamentals here. When we talked about containers, we didn't really touch on strings too much, but a string is another container. We talked about vectors and lists and things like that, and going to the beginning and the end and so on, and inserting things into a container. Well, we do the same thing with strings, and strings are much more powerful now in C++ than they were in C, because a string is a character version of a generic string container that is out there. One of the important topics or items that you want to understand is an iterator, the concept of an iterator. Iterators are used throughout all of the containers, and essentially it's a file pointer. Iterators are also used when you're using the iOStreams, so that you understand where your pointer is in the file as you go back and forth. I wanted to show you an iterator altogether here because we've kind of touched on it a few different places, but this is an example of an iterator. Here we have an iOStream, and string includes in our code, and a little itty bitty piece of code here. Here we create a new string called str, and it's going to be initialized to test string. So here's the test string value, which will be the initialization of string. And now we're going to create a thing called IT, which is the iterator, and that is a string iterator. So you see with our scope there, so we've picked up an iterator, we make a new one. So now this IT understands how a string iterator is supposed to function and what size it is, and how many bytes can be in it and so on. So here we'll set up a for loop, and we'll say that IT is equal to string.begin, and the begin method of the string class will return an iterator. So that returns an iterator into IT as long as IT is less than string.end. So this method returns the iterator that's at the end of the string. So as long as our current value in this IT iterator is less than the end, we're good to go. We can run off the end of the string without getting where we shouldn't be. And we can increment the iterator, IT++, and then we'll just use our IO stream of cout and our extraction operator with the, insertion operator into the cout and the content of the iterator. So you can see the iterator is kind of a pointer. So we use the content of the iterator and pass that information out. That's how you run from beginning to end of a string. Now again, iterators are used in all of the different vectors, lists, queues, the trees, all of the other kinds of containers that are out there. So iterators are used across the board, but they're pretty easy to understand when you look at them in a context of a string. So that's the C++ fundamental of an iterator. This is Tim Hegarty with VTC, and we're taking a look through C++ fundamentals. We are going to talk for a few minutes about operator overloading. Operator overloading allows us to redefine or overload how the basic operators in the language work. There you can see a whole list of the operators that can be overloaded, which is basically most all of them. There's just a few like the scope operator, the double colon, and the single period, and things like that, which wouldn't make any sense to try to overload. The language wouldn't work anymore. But all of these operators can be overloaded. And what that simply means is that we give them new functionality, or we give them the functionality that they need to do their job. Let's say that we create a new class that is going to have strings and string handling in it. Well, what if you add two of those classes together with a plus sign? What are you going to do? A plus is an arithmetic operation. But what we want to say is that when you're dealing with our string class and you use the plus sign on it, that means that you want to concatenate. You want to put those two strings together. If you would use a minus sign, maybe you're going to remove the first string from the second string. That all depends on what you're going to implement in the class. But to do that, that's called operator overloading. I don't know what you're going to do with a division or a multiplication in strings, but you could overload them if you wanted to. Now here's an example of a little piece of code, which is an overloading sample, and there's our little class called myString, and it has a public member called member1, so it can handle a string of 100 bytes long. I didn't say it was a very good class, but it does what we want. And there is how we overload the operator. So there's a void operator plus. And that's the key. We are overloading the addition or the plus symbol, and it's going to take in another myString value, which is a class of myString. So if we are adding two strings together and pass them into the class myString, there you see what happens. When the plus sign works, is called on to work, we do a string concatenation of member1 and plus the value of member1. So you add both of those together, and that returns back as member1. So you add the second string that comes in as the val parameter to the end of member1, creating one long new string. And that's what we have said that the operator plus is supposed to do. If we were going to define minus, we could remove the member1 from the first string. We could do an index on another operator, whatever it happens to be. But this is just an example and the syntax of what it takes to overload an operator. And again, very simple example of just overloading the addition operator. This is Tim Hegarty with Virtual Training Company, talking about C++ fundamentals. We want to talk about virtual functions and overloading. These are functions that are defined within a class, They are class functions, methods of the class, and their purpose for being is kind of a placeholder in a base class. They assume that they will be replaced in a derived class. So when we make a derived class and derive it from a base class, a virtual function can be overridden. It can be overloaded or changed. A non-virtual function, which is what we've worked with so far through our fundamentals tutorial, and I'm sure you've seen them in other places without the virtual keyword, those are not overridden. They are linked in at compile time, and those functions and their addresses are linked together hard, and that's called static linking. And whenever a class is derived from a base class and you call a function that's in the base class, the one from the base will be executed. Well, we want to be able to run the function that is in the derived class, not in the base class. So in the base class, we have to define our functions as virtual. That will allow them to be linked at runtime. So the derived classes can provide their own functionality. That's called dynamic linking. The way we do this is the compiler creates a vtable, a virtual table, as part of the class. The vtable is then populated at runtime with the addresses of the overriding functions. Let's take a look at a piece of code and try to put this together a little bit. Here we have an example. We have a polygon, and this is our base class of polygon, and it has a width and a height that are protected, but it has a set values, and that's a standard method, a public method, and it'll take two integers and set the width and the height. Okay, we don't need to change that in derived classes. That's fine through any polygon. But the area of different kinds of polygons will be computed differently. So we make that a virtual. It'll still return an int all the time, but it's going to be a virtual function. And here we just return 0. So a base polygon would return nothing for the area. It won't do any work. But when we derive a rectangle, here's a class rectangle derived from the public base, or from the base C polygon, and we use the public access specifier so that everything that's in the polygon will pass through with the same level of access security on it. And then we make new public items, members in the C rectangle, and here we're making a new area. So here we are overloading or overriding this virtual area. The area of a rectangle is the width times the height that we will return. So if we make a rectangle and call the dot area, we know how to compute that. If we do a triangle, that needs a different kind of area, and that's going to do a width times height over 2. Okay, that's a different overridden area. And again, C triangle is derived from polygon, but we can change area because area is a virtual. So you got to remember that keyword virtual if you're going to be overriding these methods in your derived classes. That's what a virtual method and overriding of a virtual method is all about.